GFIs, a couple of different rules on these. And GFI stands for ground fault interrupt. You'll hear the term GFCI, ground fault circuit interrupt. I really don't care which one you use. Shorter, 4 letters, whatever. It is what it is. These are designed to protect people. They're not really designed to protect property. Breakers, they're limit the amperage that's flowing so wires don't overheat. They're designed to protect property. GFIs, if electricity is going anywhere that it's not supposed to go, these will sense that and they'll turn the power off immediately. All right. Now, I always get mixed up on how fast these things are supposed to work. I know I've used terms of 1/50th of a second, but 1/40th is the right number that's up here. But that's just fast. 1/40th of a second is almost instantaneous. We did a couple of tests on GFIs, and I remember we had a light bulb that we had hooked up to a ground rod outside, so we created a ground fault, basically, and the ground conductors and water services. All right. So I got a question. Did you cover wire sizing for grounding electrode conductors, either by rod or by water pipe? And the answer was yes, I did. So the GEC, whether it goes to a water pipe or to a ground rod, the GEC has to either be a number 6 copper, and that's for under 150 amps, or a number 2 copper for 150 amps and over. So number 6 for under 150 amps, or number 2 if it's 150 or more. All right. Getting back to the GFCIs. They need to trip off quick. We set up our sample. We put a ground rod out in the middle of the yard. We connect our neutral wire to that. We put that to the neutral side of a light bulb. We ran a hot wire to a switch, and then the switch to the hot side of the light bulb. And we had that hooked up to a GFCI outlet. All right. We flipped that switch, and as soon as we flipped that switch, that GFI tripped. We couldn't even get it to flash. We couldn't get it to even blink. As soon as we flip it, we hear the click on the outlet. It's that quick. So basically, hardly any power at all is going to be going through these things. 5 milliamps difference. That's all it takes. All I have to do is lose 5 milliamps of power, and that's going to be enough to cause these, whether it's the breaker or the outlet, cause the GFCI to trip. All right. Basically, it checks for an imbalance between the hot and neutral. This works on the same principle. Let me bring up the next slide. This works on the same principle that I mentioned earlier, that it expects the amperage that's on the energized conductor to be identical to the amperage that's on the neutral conductor. All right. So I'm going to switch cameras here, and I should have cleaned up while I had the chance. Maybe. All right. Let me go ahead and get rid of my mess here. Okay. So let's say I got, and I need you to use a little bit of imagination here. So even though I'm drawing on the whiteboard, I want you to picture this as a bird's eye view. So we're looking at a table coming straight down here. All right. So as I look down, I drill a hole in the table, and I run a single electrical wire. That's what the red dot is coming through here. And this way here, north is pointing up at this point in time. All right. If I put 4 compasses around this wire, and this wire right now is not powered up, all of those compasses are going to be pointing north. Because again, the Earth is a gigantic electromagnetic generator. We have a north pole and a south pole. They're going to go to the positive side of the Earth, which is the north pole, and that's where they're all going to be pointing at. But now if I have this single wire all by itself, and now I energize it, all right, so now it's got power coming through it, and there's no neutral wire that comes in here, all of these compasses are now going to be aimed at that wire. That wire is creating an electromagnetic field that comes in there, all right? That's basically what this, and I'm going to switch back. That's basically what we're looking at in this diagram here. That ring where the 2 wires go through senses for that electromagnetic field that's being created, all right? Now going back to the drawing that I had before, if I took a neutral wire and I twisted it together and I kept it back in there, all those compasses would point back to north again. That neutral wire would cancel itself out, all right? So as we're looking at this diagram, and this is a GFCI, it is in use, it's closed, so power is on, and everything's normal, all right? So we see energized power coming in, it's going to its load. Load is wherever the work is being done, all right? And we said amperage does not disappear. So if 2 amps goes in on the hot and 2 amps go out on the neutral, I am creating a zero magnetic field in that ring, all right? Let's go on to the next one. So now we're showing that I have some sort of a ground fault, all right? So same things. I got energized conductor coming in. 2 amps is going in. 1 amp is going to the earth. And remember, it could be as small as 0.5 of a milliamp, all right? Or 5 milliamp coming in there. Electricity is going someplace it's not supposed to go. These GFIs don't know where it's going, all right? They just know it's not coming back on the neutral. Now I have an imbalance between my hot and my neutral. When there's that imbalance, those compasses now, because I'm creating an electromagnetic field at this point in time, that sensor will sense that and instantly open up that circuit, turn the electricity off to that circuit, and then turn the power off. So as long as the power is off, nobody gets hurt. All right, if the power's still on, then people get hurt, all right? And a lot of people say, well, what about these testers? Don't they, let me go back to that one there. What about these testers? Don't they, just trip the mechanism and that's it? They don't, all right? If you look at the routing from where the test button is, you could see that as we start, right here at this dot, we're going to go through when we test that button, and we're going to come back, and this resistor is going to allow 0.5 of a milliamp. So it's going to be the bare bones minimum, and it's going to bring it outside that ring. This ring is supposed to sense that difference and open up the breaker and turn the power off. So those test buttons don't just flip the switch. They actually create an internal ground fault in there. Same thing with our testers, all right? And that's another clue. If you press that test button, the GFI could be bad. They do go bad. But they might also have a bootleg ground in there, all right? So if we're going ahead and taking the electricity and putting it on the ground, and then the ground is putting it back on the neutral, it might not be able to sense that, all right? So if it trips with the button, we know the GFI itself is working, but we may not have the proper connections inside that outlet as well. And that works for everything downstream. So line and load, a couple more words that I guess we should know. Line side, anything that goes towards where the power is coming in from, that's the line side. Doesn't matter where I draw my line at, you know. In this case, we're going to take that GFI outlet. Anything to the power source is the line side of that outlet. Anything to where the work is being done is going to be to the load side of that outlet. That GFI is going to measure the amperage in all of those outlets, everything that's on the load side, including itself, when it's measuring the amperage, all right? So let's say that the GFI outlet at the top is using, I don't know, I'm just going to make up numbers, 2 amps. And then, so this one will be a 2, all right? And then the bottom one there is going to be another 2, and then this one will be a 1, and this one will be a 3 amps, all right, that all these things are using. So that would be a total of what, 4, 5, 8 amps, all right? So that GFI knows that 8 amps is going out, 8 amps should come back in. So even though all those outlets to the right are not actual GFI outlets, they are GFI protected. These outlets or breakers will protect everything on the load side of them, including themselves. All right. Arc faults and arc fault circuit interrupters. First thing I think before we talk on these, it should be known that the city of Chicago is not mandating that arc fault circuit interrupters be installed. All right. Most of the suburbs, at least I'm not aware of any of the suburbs in Chicago or any place else in the state of Illinois. And, you know, I hope you understand, I do not know every single code in every single part of this state or country. All right. So if some of them are following suit of Chicago, that may be true. But not everybody, or the city of Chicago itself, does not require arc fault circuit interrupters. Their rationale is everything is in conduit. They have some of the safest electricity in the entire nation. I believe they're actually accurate. And the amount of damage that could be caused by these things, they feel that it's limited, so they don't want to spend the extra money and undue cost to go ahead and put them in there. It's their choice, and I'm going to respect it, plain and that simple. So what an arc fault does, it tends to provide protection from the effects of an arc fault. So basically, it recognizes that sine wave and when something is going a little haywire or hokey with it. All right. I think it's safe to say there's 2 types of arcs when we're dealing with our electrical system. All right. What are we saying? Arc is a discharge of electric current across a gap. So anytime electricity is traveling through the air, basically, that is an arc when it comes to it. A lightning strike is an arc. All right. If 2 wires are close enough together and it's sparking across those, that's an arc. All right. It's a discharge of electricity. Parallel arcs can get extremely hot, but even the series arcs can get up there as well. It all depends on the load and how long they're going. It's a spark. All right. Any type of spark can go ahead and create some sort of a fire. So it expels metals when you see these things, and hopefully they'll evaporate. All right. So 2 different arcs I want you to be aware of. Series arcs and parallel arcs. All right. Series arcs are typically going to be the energized conductor. All right. So if there's a nick in it or a separation of the wire itself, and still enough to go ahead and get sparking, so electricity is still going to flow, that arc is only going to be as powerful as the load that's being used on it. So if I have a 120 watt light bulb being used on this series arc, then at 120 volts pressure, it's 1 amp. That arc is going to be basically 1 amp. All right. The more electricity that I use, the more powerful that spark or that arc is going to be. Whereas parallel arc, that's going to be my energized conductor and my neutral conductor. And this is what we mostly see. When they start getting smushed together and getting close enough together, then they're going to want to start creating a short circuit or a phase to neutral fault, when it comes with it. So how this happens because we know we have conductors, we have insulators around the conductors, and then with extension cords, basically, I got 2 conductors. Both of them have insulation in them. Then I got another sheath that wraps the whole thing together. If I keep stepping and standing on that sheathing and I just keep squeezing it and breaking it, I mean, if you think about it, over time, I'm going to be damaging the insulation on the conductors themselves and the sheathing with it as well. And if I just keep squeezing it and squeezing it and squeezing it, and it gets weaker and weaker, electricity is going to eventually want to start making its way through the insulation once it gets damaged, and it's going to start creating a parallel arc at that point in time. Now, if it's bare bones metal on metal, then we're going to have an unlimited flow of electricity, and most likely my breaker will trip. But before I get to that point, I might just have a breakdown in insulation. So I might only have 20 amps on a 20 amp breaker that's jumping across these things, and it's constantly making sparks. And then all of a sudden it actually ignites the insulation. Or if it sparks and gets to an opening in a junction box or an electrical panel, then that could get to the wood structures of the properties. And I know most of us look for holes in electrical panels and outlet boxes and stuff like that. And I think a lot of people explain to you, look for the holes so that you're worried about people sticking their fingers in there. And, really, I've never heard of anybody sticking their finger inside of an electrical panel and getting shocked. What I have seen with my own eyes is that we create an arc or a fault inside this. We create an arc and sparks start flying inside those panels or inside of a switch box, and those holes are missing. Now those sparks get out of that panel, because those panels are designed to contain any sort of blast or arc or fault that happens inside of them. But if those holes are missing, now it gets out of there. If I got insulation, wood, anything else, there's a chance that it could start the structure of the house on fire. And that's where it comes with it. So simply making sure that all those openings are filled, it's an easy thing to fix, and it's an easy thing to look for. And granted, I get it. The planets have to be in alignment. I got to have a hole. It's got to be enough to where it ignites the wood. I got to have an arc. But that stuff has happened. And it's happened, enough times, which is why we make sure all these things are sealed. And quite frankly, I think it's a pretty cool thing that we get to do, because we get into everybody's housing inventory in the entire state of Illinois. And for simple little plugs or fill-ins, we could do everything to keep those sparks from getting out. But anyway, I'm jumping on a soapbox. I do want you to know the difference between a series and a parallel. Series is one hot wire coming apart. Parallel is the hot and the neutral pushing together. All right. Series, less likely. Current load is limited because of whatever the work is being done. Series arcing cannot be greater than the current of the load, but it still produces fire. It can still create a spark. It still produces molten lava. It still sparks, any way you look at it. Series arcing did not develop enough thermal energy to create a fire. I disagree with this statement, plain and simple. Parallel arcing, they are the most dangerous. That much I'll get. Unlimited energy until the breaker is turned off. A parallel arc is created by a short circuit or ground fault, something that's going to go ahead and start getting everything to be, getting the insulation on the conductor's ruined. Now that could be whether it's an extension cord, or here we're using non-metallic cable or Romex, anything that could go ahead and damage it. So here I got a lamp cord going through a doorway. Every time that doorway closes, it's going to keep pinching that lamp cord, wearing away at the insulation until eventually it's going to create something that can go ahead and ignite that whole thing. Here, this is just a drawing I got off of, I think it was this old house or something like that. But nails going through non-metallic cable, and they can also start creating some sort of arc fault underneath there as well. This I think is a little excessive. Again, it was this homeowner's talking about safety, of which But if you take something that is grounded, so that drill that he has in there, so the bits, everything else, that he has a ground plug tied into it, now he goes into the energized conductor of that wire, you're going to be creating a short circuit and you're going to get sparks flowing. All right. Mostly what we're going to end up seeing is the damage of the insulation that comes to it, and that's what we're looking at here.